this one. Okay, we do not need to talk about quantized stuff for you guys. What am I doing? New one. Okay, here we go. So today we're going to start talking... Oh, announcement, I guess. Well, hold on. I'll let you guys trickle in. And then we'll have announcement time. I'm just getting too excited. So, let's see. Okay. Cool. Yes, good morning. You guys are always so much more energetic than my 101 class. I guess the 10:15 time slot is better. Okay, cool. So, announcement time. So for those of you who may not have paid attention in Discord or whatever, things annoying me. Okay, there we go. Thursday, we are going to have a exam review. So how that's going to work is I'm going to ask you to take screenshots of exam questions you'd like to go over, and then on Thursday I'll have you post them in our Discord and we'll go over them. Unfortunately, you won't be able to say, hey, can you just go over number 5 or whatever, because how this one works is things are going to be randomized, so your number 5 will probably not be the same as anyone else's number 5. So, you'll have to actually do little screenshots. And so, yeah. So on Thursday, we'll do that. Totally optional. No new information on Thursday. So we'll just have a kind of addressing any misconceptions that you guys may have or something, or if there's any particularly difficult problems, we can do that. You guys also did ask if stuff is cumulative, and so my answer to that is some of it will be and some of it will not be. So stuff like empirical formula, or counting the neutrons, or some of the more kind of esoteric stuff like that is not going to be on your future exams until the final. So you are totally free to just eject that from your brain and then panic come December and be like, oh crap, why did I forget all that? However, stuff like unit conversion and metric units and chemical reactions, that stuff is going to follow us for quite a while. So that stuff will still be necessary. Okay. Cool. So that's it for announcements. Average was pretty high on your exams, so that's great. 3 students, by the way. I have on Canvas. I have made it so you can go back and see your answers and the correct answers. So if someone at some point during this can go double check that you guys can see that, that would be great. Just to make sure. So you guys should be able to see it, so you can screenshot it. Let's see what else. No, I think that's it for announcements. So we're going to continue talking about chemical reactions right now. So, we're going to have, in chemical reactions, we're going to have kind of 4 states of matter that we're working with. We're going to have solids, liquids, gases, and the last one is the aqueous one. Okay, awesome, Kevin. So, oh, by the way, so normally I do normalize the exam, meaning that if the highest score is 95%, I make 95 the new 100, as it were. So, but however, we had a number of students, 5 of you got 100%, which is awesome. So there will be no adjustment this time. However, on future exams, if the highest score is not 100, then everyone will get a little bit of a boost. So that is what I do to address, if I make it too hard or something, that's how I address it. So, if everybody gets a 30%, then everybody gets 100, yay. But that's not going to happen, so sorry. Cool. So, in reactions, we can have solids, liquids, gases, or the aqueous state. Oh my goodness, I did not write aqueous. This is going to be kind of the a very common one in a lot of chemical reactions that we do in Gen Chem is the aqueous state. Just because to get a lot of things into gases, it can be pretty high temperature, or we need to have certain pressure things going on that's a little bit more complicated. Solids are very boring; they don't really react unless we dissolve them, or they just react on their surfaces. But liquids, liquids are just not as common. So aqueous is kind of the big one for us. And what this aqueous means is dissolved in water. And so we're going to see that a lot of ionic compounds and covalent compounds will dissolve in water. Water is, at least in Gen Chem, known as the universal solvent. It dissolves a lot of things, right? So, because if we were to put, let's see, I'm just going to draw some sodium chloride here, quite inefficiently. We're going to see that when we put this chunk of salt into the water, what happens is we're going to end up getting let's see. We're going to end up having water kind of pulling apart these ions. It's going to separate them. And so if we were to take that and put it in chemical reaction form, if we were to say, okay, I've dissolved this in water, we describe that in shorthand by writing aqueous. What this really means is we are actually breaking it up into the respective ions. So this is kind of shorthand here, and this one is expanded. So what we understand when we say an ionic compound is aqueous, we're understanding that it has split up into the ions that form it. And so if we were to have another one, say if we were to dissolve the calcium chloride in water, that's going to split up into its ions as well. And notice now we have 2 chloride ions that came out. Sorry, let me just adjust this a little bit. Okay, so we're going to see that we're going to have 2 chloride ions and 1 calcium ion that come out of this compound. And just for one more, if we had aluminum nitrate that we were to dissolve, that would break up into an aluminum ion plus 3 nitrate ions. So notice here our polyatomic ions aren't breaking apart. We're not breaking into nitrogens and oxygens. Polyatomic ions kind of stay together. So we're not going to break that into N3 minus and O2 minus and all that fun stuff, right? Polyatomic ions are going to kind of stick together. Okay, so we're going to have to learn a few rules for predicting whether certain things are going to be soluble or not in water. And so, soluble. Very often you're going to have solubility charts. I will put one up for you guys so you can kind of see. But as a rule of thumb, I'll give you some just kind of quick and dirty, like is this soluble or not. So some soluble ones will be anything with sodium, potassium, lithium, ammonium, nitrate, or acetate. So anything with any of those ions is going to be soluble in water. Okay, so if it has one of these guys as part of its makeup, it will be soluble in water. We're going to see that anything with chloride, bromide, or iodide will also be soluble, except in angry red. Oops. If it has silver, mercury 1 in this case, or lead. That means that, for example, we would expect calcium chloride to be soluble because it has a chloride in it, but silver chloride will be insoluble. Does that make sense? So anything that has a chloride, bromide, or iodide should be soluble unless the cation is silver, mercury 1, or lead 2. Okay, so this is telling us halides. That's what these are. Halides are soluble unless they are halides of silver, mercury, or lead. Our last kind of happy one is going to be anything with sulfate except calcium, barium, lead, and is mercury going to be one of these? I think it is, yeah. All right, so our sulfates that are not going to be soluble would be calcium sulfate, barium sulfate, lead sulfate, etc. So we would expect something like cobalt 2 sulfate would be soluble, but calcium sulfate we would expect to be insoluble. Okay, so we kind of have three classes of soluble compounds, and then we have some exceptions to those. Okay, so this is kind of generally what we're going to understand something to be soluble or not. Okay, these are ionic compounds only. So things that are made of ions, metal, non-metal, right? Or metal polyatomic ion or something like that. We're going to have rules for that. Oops. We also have one more thing to say. We have a couple of ions that if they are put with something would be insoluble. Except with the same thing from the first part, the sodium, potassium, lithium, ammonium. Okay, so things that have carbonate, hydroxide, or sulfide are typically not soluble. Except, of course, if they have sodium, potassium, lithium, or ammonium. So just like before we said anything with those guys will be soluble, I'm not changing that rule. Anything with sodium will always be soluble. However, we're going to see that most carbonates, most hydroxides, most sulfides are insoluble. Okay, except if they have one of those four guys. Okay, so with that in mind, let's do some practice here. And if something is not on this list, yeah, soluble means it will split up. So, I mean, you guys kind of know what soluble is, right? If you put salt into water, you're going to see it kind of vanish, right? Just visibly. If you put something like chalk into water, it's not going to dissolve. It's going to stay as that chunk of rock at the bottom. And let's do another one. How about this one? Okay, cool. So, looking at this, nickel 2 sulfate, what do we think about this? Do we think it's going to be soluble or insoluble? Wait a second. I've done something bad. Okay, let me add a couple more. Let me erase that one. Oops. Okay. First line. Which ones are going to be soluble? Do we predict? Yep. So I'm going to actually, yeah, I'll write soluble. Next. Sodium carbonate. Just give me the whole row. Yeah. Potassium sulfate. Yeah. Next row. Iron 3 nitrate. And copper 2 acetate. And lithium hydroxide. Yes, they're all soluble. That's why I said, whoops, I made a mistake, because I made everything soluble. Alright, and just in the interest of time, because I had, been, oh crap, I made everything soluble, this one is, oops, actually all three of these are going to be insoluble. Yes, those are all insoluble. Okay, so again, you could refer to those rules up there, but I will post a handy-dandy chart. How the chart is going to work is you're going to have cations on one side and anions on the other side. It'll be like, X and Y axis. You'll find your cation, you'll find your anion, you'll see where those two meet, and it'll say if it's soluble or insoluble based on that. Aha! So, for two rules, so definitely this one at the top says anything with sodium is soluble. There are no exceptions. And then we have this handy dandy little thing here in green to remind us that carbonates will be soluble if they have one of those four guys, and sodium is one of those. So we're not contradicting any of our rules here. So that's why sodium carbonate will be soluble. Okay? No worries. Okay, so what happens with these things? Yes, it will have the rules on them. Well, not these rules. These rules are kind of just like, it's a different way of presenting it. So these rules are a written way of talking about these compounds. The chart is more of a visual way. So you'll see it, and you can use either one. You could either use the rules or the chart, or both, I guess. So yeah, whichever way you like is fine. Okay, so with that in mind, we have something called electrolytes, which are things, if we can analyze the word electrolytes, electro meaning, electricity. It's technically electron, but we'll say electricity. And light means broken or like split. What this means is something that conducts electricity when split apart. So, if you happen to be, I guess it doesn't really happen in California too much, but if you're, silly and you have a thunderstorm, lightning is happening all the time, and you are, for whatever reason, wanting to go into the pool, not a good idea. If your pool is full of distilled water that does not have electrolytes in it, you'll actually probably be okay, because that water will not conduct electricity. However, as soon as you put in an electrolyte, it's going to conduct electricity when it breaks apart. And what that means is we're going to see that soluble ionic compounds are strong electrolytes. So what that means is they break up in solution, and we know that because they'll be able to conduct electricity. So electricity is electrons moving around, right? And so if we have ions, the electrons are going to be moving kind of between the positive and negative. They can just kind of go through, be attracted to positive ones, be repelled by negative ones as they go around. And so we're going to see that all of these soluble ionic compounds are going to be strong electrolytes. They break up completely in solution. I forgot an E there, didn't I? Completely. We're going to have, this is normally a demonstration I would do. I would show you guys with an electricity conductor, or we'd do a lab on it or something, but not right now. COVID, it sucks. We have what are called weak acids. Actually, hold on. Strong acids are also strong electrolytes. We're going to have 6 acids. These 6 guys, when we put them in water, yes, screw COVID. When we put them in water, will break up completely as well. What this means, if we put our nitric acid in water, it's going to completely break up into hydrogen ions and nitrate ions. So these 6 are special acids. These ones will break up completely. So again, strong electrolyte means they break up completely in solution. That means in water. We're going to see we have weak acids, which if you take C113 Gen Chem 2, will be the bane of your existence. You'll hate weak acids, which are going to be all other acids, are going to be weak electrolytes, meaning they break up a little bit. What that means is we have something like acetic acid. Notice I've put this double arrow here, one going each direction. That's because this is a reversible process. At any given time, we'll have about, a 99% of the acetic acid will be in that form, and about 1% will be in this broken up form. And so that's what we mean by it breaks up a little bit. So if you were to have 100 molecules of acetic acid, maybe one of those molecules will have broken up into H+ and the acetate ion. The rest of them will still be hanging out as acetic acid together. And so these will also just kind of conduct electricity a little bit. Okay, but these guys we're not really going to mess with right now. This is more for Gen Chem 2. So we'll be talking about these guys quite a bit more in Gen Chem 2. We also have what are called non-electrolytes. They dissolve, but do not break apart. And what we're going to see here, this is going to be polar covalent compounds. We're going to learn later how to determine if something is polar or not. Yeah, exactly. So sugar. So we know this is not technically sucrose, but this is glucose, right? That dissolves in water. We can get sugar to dissolve in water, but it's not going to break apart. It's going to stay as sugar. Or something like ethanol. We know that ethanol dissolves in water. It just doesn't break apart. Yep. So the water will just kind of separate. So you know how these solids kind of exist as crystals? The water will just kind of surround. Okay, here. I know that you said never mind, but I'm going to do it anyway. So in sugar, you have all these happy, in a solid, they're kind of arranged nicely, right? And instead of them being, differently charged, we're going to have, again, kind of a lot of waters surrounding a particular sugar. They're going to have enough stuff on there that the water will still be attracted to them. And we're going to just have a lot of these things floating around in there. So they just don't break apart. You could have other things like formaldehyde. A lot of these kind of covalent compounds. Sand does not dissolve in water. So electrolytes dissolve, but they don't break apart. So they're still soluble. They just don't break apart. Okay. Let's just put formaldehyde on here. Yeah. So this is all stuff that dissolves. Okay, obviously insoluble stuff will, things remain solid. They do not break apart. So, for example, we can have a reaction here. What's going to happen here is we understand that this is made up of sodium ions, carbonate ions, calcium ions, and chloride ions, right? Technically, we have 2 of each of those. Let me just erase those, though. We'll deal with that later. This is another type of reaction we're going to have in which the kind of pairs swap partners. So sodium was with carbonate. It's going to now go with chlorine. And calcium that was with chlorine is now going to go with carbonate. We're going to see that sodium chloride should be soluble in water, right? No surprises there. However, calcium carbonate is insoluble. This is insoluble. Does not break apart. And so we're going to see this will be another type of reaction called double displacement, which is also called metathesis, which just means exchange. They're swapping partners. So sodium that was with carbonate is now going to be with chloride instead. Calcium that was with chloride is now going to be with carbonate instead. So you just swap the anions or the cations, whichever ones. Just make different partners. Alrighty, so notice that what's happening here is we have kind of just ions floating in solution, right? We have sodium ions, carbonate ions, calcium ions, chloride ions. What happened in this reaction is, let me go ahead and put in our states of matter. Right, calcium chloride and sodium carbonate are both soluble compounds. Sodium chloride is soluble as well, but calcium carbonate is not. And just to annoy you, for insoluble, we write S for solid. Right, it's not soluble. S for solid, not for soluble. I apologize for that, but I didn't make the rules. So what's happening here is that the calcium carbonate, or rather calcium, these guys like each other. More than they like water. So we saw that when something dissolves, the water is going to kind of surround it, right? So when the sodium chloride dissolves, the water is surrounding the sodium, the water is surrounding the chloride. That's, favorable. In this case, the reason that calcium carbonate is insoluble is because calcium and carbonate like each other a lot more than they like water. So they would rather be together than be surrounded by water molecules. So just physically, that's what's happening. It's not, of course, they don't have emotions or whatever. They're not like that. But it's just in terms of energy, it's less energy for those guys to be together than it is for them to be with water. And as we know in chemistry, everything wants to be as low energy as possible. Of course you will, Tyler. That's the whole point of talking about all this solubility stuff. So, again, this will be something you'll have plenty of practice on. Don't you worry. We're going to see that we have ways of talking about this more specifically. But let's do a couple more examples. Let's see. Let's see if we can predict the products first. So notice my compounds are always charge balanced up in here, right? So if you think about it, this guy is made of 3 potassium ions and a phosphate ion, right? This one is made of an aluminum ion and 3 bromides. Remember, in this type of reaction, we are just going to swap the partners. So, potassium used to be with phosphate, now it's going to be with bromide, right? In this case, we're going to have 3 of them, right? Because just balancing, we had 3 potassium ions, 3 bromide ions. And as someone has said, this guy is going to be not soluble. Did I put phosphates on your list? Oh, I didn't. Okay, that's another one that's typically insoluble. Most phosphates are insoluble. But generally also, because it's not listed as one of our soluble ones, I mean, this rule here is not really telling us anything new. This last rule here, it's easy. You can just follow the first 3 rules too. Okay, sorry for that. So phosphates are definitely insoluble as well. Notice that we do not have, if you ever do this, this makes me very angry. Never, ever, ever do this. Why do we never do this? We must remember that we have to always charge balance properly. So potassium, charge of +1, bromide, charge of -1, we only need 1 of each. If you write it K3Br3, that means that we have some sort of polyatomic ion that's, yeah. It would be some weird polyatomic ion thing that doesn't exist. So we will never write it that way. We must always charge balance properly, and then we can balance later. So this is a big no-no. It's gonna get deep blue no-no. Okay, so never, ever, ever write that. Okay? So we also notice that at the end of the equation, we still have these guys plus the aluminum phosphate. And just using the color, that's going to be solid, right? So, do we remember algebra that, hey, look, this guy is on both sides of the equation. And so are the 3 bromides. We're seeing that as the reaction happens, these guys are not doing anything. They're not changing. It's exactly the same on each side of the reaction. They were exactly the same. And we're going to call those spectator ions. They're exactly the same on both sides of the reaction, and so they're not doing anything. There's no chemical change that's happened with potassium in this example. Nothing that's happened with bromine either. So those guys are spectators. And if we get rid of spectators, we end up with what is called a net ionic equation. In this case, that's going to be If I just write out the whole thing, that's going to tell us that the only thing that's really happening here is a phosphate ion and an aluminum ion are coming together to make aluminum phosphate. This is what's happening overall in the reaction. The potassium and the bromide are not doing anything. They are spectators. They're just hanging around. They're there to charge balance things, but they are not doing any other chemistry. However, we're seeing that with phosphate and aluminum, those guys are actually doing chemistry. We're having a chemical change happening there. They're reacting together to form a solid. No, not really. So catalysts we're going to see in 113 are going to be substances that kind of speed up a reaction. They make it more easy for a reaction to happen. These guys, the potassium and bromine, aren't really helping the reaction to happen. They're just there because something needs to be there to balance out phosphate. You can't just have phosphate by itself. You have to have something positive to balance it out. There's always a balance of positive and negative in real life. We could always swap out those spectator ions, by the way. We could have made it sodium phosphate and aluminum chloride, and we would still end up with the same net ionic equation. So our spectator ions aren't really doing anything. They're just there. They exist. That's it. So, but they're not helping things happen. They're just there. Okay. So let's do one more, just because. Let's have. Yes, let's do this one. Let's see what our products are going to be here. So putting these guys together, what are we going to expect as our products? Just like always, we are going to take our other pair and put them, or our cation from one, anion from another, put those together. So we should make sodium sulfate. In case we've got two of them. What's the other product going to be? Remember to charge balance properly. What happens? Yeah, exactly. We're going to get HOH, right? H plus, OH minus. Those guys come together to make HOH, but nobody writes it HOH. We prefer to write it as water, right? H2O. Notice here that water is a liquid, yes? We know that. When we form water, it's typically a liquid in a reaction. You'll probably notice, hey, things aren't quite right. That's because I haven't balanced this. We should get two H2Os. And so now things are balanced and we're happy. So obviously water can't be aqueous, right? We can't have water dissolved in water. I mean, doesn't really make sense, right? So let's have a look at what our spectator ions are here. What do we think the spectators are going to be? What is exactly the same on both sides of the reaction? By the way, when we split it all out like this, it's called a complete ionic equation. That means all aqueous are split. So just definition there. Yeah. So sodiums and sulfate are going to be our spectator ions in this one. So if we remove them, our net ionic equation is going to be 2 hydroxides plus 2 H pluses. Hydrogen ions form 2 waters. Remember, our ions are going to be aqueous, and our water in this case will be a liquid. Okay, so all that's happening here is we have OH minus and H plus coming together. They're making water. Poof, done. Alrighty, any questions on how we predicted the products for that equation? Okay, I don't see any, so that's good. We're going to have we're going to have some sort of observational types of reactions here. We're going to see if we get a solid as a product of a reaction, we call it a precipitation. So that's just telling us we have formed a solid in our reaction. Excuse me. If we have formed a liquid, we call it neutralization or acid-base. And typically that's going to be water. That's pretty much the only liquid we're going to get out of a double displacement reaction. And while we have not done any that form a gas yet, we call those gas evolution reactions. Evolution means like it's coming out. So if you have mixed your vinegar and baking soda, you have done a gas evolution, right? Your volcano from 3rd grade or whatever is going to be bubbles that are forming. That's typically seen as a bubble. How we're going to know a neutralization reaction, it also often heats up, and solids are going to look cloudy when they're formed. So you're forming little parts of solids in there. As soon as you have solid, it's going to look cloudy. You're not going to all of a sudden see a piece of chalk at the bottom if you make calcium carbonate, but instead you'll see little particles of it, and that's going to make it look cloudy. So bubbles are going to be our gas evolutions. So we predict precipitation, using our solubility rules. Okay, we can predict neutralization when your net ionic equation is going to be H plus and OH minus coming together to form water. Again, typically that means there's an acid and a base together. Many bases for us will be hydroxides. We will also have other types of bases, but an obvious one for us will be if it's got a hydroxide that's a base. And acids, as we know, have H plus on them. So that's going to be when we're going to see a neutralization reaction happening. And then we're going to see if we form one of 4 options here. There are 4 options that will be gases for us. Hydrogen sulfide is a stinky gas, rotten egg smell, that can be produced in a reaction. We'll see an example of that. And anytime we see something that makes one of these 3. These guys are unstable and they decompose. So just to illustrate those reactions, when carbonic acid is formed in a reaction, we're going to be producing carbon dioxide. That is a gas. That is going to be bubbles. So when you open your soda can, that's the bubbles coming out. That's carbonic acid breaking down into water and carbon dioxide. These 4, unfortunately, you're just going to kind of have to commit to memory. Or again, since this is open note, have them written somewhere. But anytime you have one of these 4 things, you're going to be having a gas that's produced. The sulfurous acid will behave very similarly. In this case, you'll get sulfur dioxide as your gas coming out. And then the last one, ammonium hydroxide, you actually form, let me be consistent here, you form water plus ammonia gas. Okay, so anytime you see these 3 in a reaction, or any of those guys, break them down. Okay, let's see what this is going to look like. Let's do your classic baking soda plus vinegar, which is also, by the way, it's also a neutralization, but more importantly, it's gas evolution. So when you put these 2 guys together, remember this is made up of sodiums and bicarbonate ions. This is made of H plus and acetate. If we now put sodium with acetate, we'll get sodium acetate. Oh, fun name. And if we put H plus and HCO3 minus together, note that we get carbonic acid. Ooh, I don't know what that is. Okay. And remembering this from before, that this guy is automatically going to break into water plus carbon dioxide. So if I were to ask you to predict the products of this reaction, you should give me all 3 of these. You should give me sodium acetate, you should give me water, and you should give me carbon dioxide. You have 3 products in this case. So technically, through this double displacement, you're making carbonic acid, but that carbonic acid immediately will break down into water and carbon dioxide. And we can tell because if you mix baking soda and vinegar, that's these 2 compounds, you'll see the bubbles. It's happening. You can see the bubbles. It's going crazy. It's made your volcano. Your kids are happy. It's very exciting. Definitely this is happy, safe chemistry you can do at home. Good for cleaning your drains out or whatever. Happy reaction. Similarly, if we had another one, like, let's say, this reaction, again, swap your partners. We're going to make lithium chloride plus ammonium hydroxide. But remember that this guy needs to be split up into ammonia and water. It does not matter, by the way, which order you put these in. You can put water first, ammonia first, lithium chloride first, whatever. You should get these three products out, though. Okay, and how you're going to know this one. So ammonia doesn't bubble as much, typically because this is it's pretty soluble in water, but ammonia stinks, right? It smells like ammonia. Don't sniff ammonia, by the way, it stinks. But if you were to do this in lab, you could tell this is happening by gently, kind of smelling it. You can smell the ammonia very, very strongly. So that's how we know it's there in its gas form. Okay, and an example of another one would be, I don't know, we could put these two guys together. We'll get technically I should balance this, but notice again we have one of these compounds that we need to know, and that one will split into sulfur dioxide and water. Just so we remember, we should be good chemists and continue to indicate our states of matter, which your instructor has not done. So I'll quickly go and fix that before anybody catches on. So these would be, I have one more to do for you, sorry. And then I'll ask for questions, because I know this is, again, a lot of information. Let's say we had let's do something else. Let's use HI instead, so it's not all the same. Aha, notice this time we're going to get hydrogen sulfide and ammonium iodide. Anytime you see hydrogen sulfide, you just have to remember that that is going to be a gas. Okay, so hydrogen sulfide is not something that's going to decompose and turn into a gas later. It's just a gas already by itself. Okay, so there's 4 times you'll see gases in a double displacement reaction. So you'll have carbon dioxide, sulfur dioxide, ammonia, hydrogen sulfide. The first 3 of those will come from something decomposing, and the last one is just going to be a gas by itself. Okay, so far water is our only liquid that's going to be formed, and we have 4 gases, and we have a whole bunch of potential solids depending on the ions that are forming. So guess what? We're going to have homework on this. Hooray! And so tomorrow we are going to continue on talking about another type of reaction, our last type, which is single replacement. We're going to talk about oxidation numbers, which is how we're going to do some electron accounting. That's probably all we'll have time for tomorrow. Thursday we'll have our exam review, so that's optional. And then Monday we'll finish off the chapter by talking about stoichiometry and solutions. Everybody's favorite. So don't think stoichiometry's done. Don't think you're done with that at all. So that will be back for sure. And then after that we'll start thermochemistry, which is something you'll hate. Actually, you'll hate everything in this class, but thermochemistry is fun. And then after that, we're talking about electrons. Yay! Cool. Yes, rage indeed. So, I'll be posting up homework for these double displacement type reactions. So yeah, we'll have that. I'll post that later today so you guys can have fun. Because, you know, your brains are not already dead from the exam. So, cool. Okay. So I'll see you guys tomorrow. As always, put stuff in Discord if you guys have questions. And I'll see you then. Take care.